had to pause the video and correct something I forgot, that I had a transition using B from here. So let me erase this. So back to where we were in the B column. Hey, where can I go from Q0 with input B? From Q0, I can take input B and I can go to Q4. Okay, and then I want to grab the, there's no other places I can go from Q0. Let's grab with input B, so let's go to Q2. Q2, input B, nothing. So this is where I want to do my lambda transitions of Q4. So it looks like I might have to kind of go up here, Q3, Q0, and Q2. And let's put this on this side so it doesn't confuse us. Okay, and then every time I create a new, basically if this is different than anything else in these boxes, I gotta put it over here in my transition states. So Q1, Q0, 1, 2, 3, 4, 5. I have that over here. Now I have a new one. It's going to be called, it's basically Q0, Q2. I'm going to put them in order just to make it a little nicer. Q3 and Q4. So every time you generate a new collection of states, you need to make sure they're all listed in this column. So we could keep going on and on. I think for this example, this is going to be the last one. Okay, so now let's go to over here. So with Q2 input A, Q2 input A, I can go to Q5. Q1 input A, I can go to Q5. Q5 input A, don't go anywhere. Q4 input A, I can go back to Q1. Q3, where can I go with input A? From Q3, input A, can't go anywhere. Q0, input A, where can I go? I can go to Q1, I already have that. Now we have Q1 and Q5. Let's also go down here, find our lambda closure transitions. So Q5 basically has everything. So Q1, Q0, Q2, Q3, and Q4. Okay, now with our input B, same thing. From Q2, where can we travel to with an input B? Nowhere. Let's go to Q1. Where can we travel to with input of B? Or in this column here, we can travel to Q2. Q5, where can we transition with input B? No direct transition. Q4, where can we transition with an input of B? Nothing. Q3, transition of B, there's nothing. Q0, we can transfer to Q4. Then we have our lambda closures that we need to find of Q2 and Q4. So Q2 is just Q2. Q4, we have 4 and 2, we're missing 3 and 0. Q3, Q0. And you can see these guys, and this is all matching, so we don't need to add anything yet. Input A, Q0, we can go to Q1. Input A on Q2, we can go to Q5. Input A on Q3, no direct transition. Q4, input A, no direct transition. Now let's find our lambda closures of Q1 and Q5. Q1 is just Q1. Q5, looks like we have everything. So already have Q1 and Q5. Let's have Q0, Q2, Q3, Q4. Okay, so Now that that's done, let's transition over to input B. So Q0, input B, no direct transitions. Q2, input B, there's nowhere to go. Q3, nowhere to go with an input of B. Q4, no, nowhere to go. So, actually, let's double check this. Q0, oh, Q0 on B, we can go to Q4, whoops. Q2, yeah, so that's correct. And the transition of Q4, we got Q3, Q2, Q0. So now our table is complete. So P0, this is going to be a state. This is P0 right here. P1 is going to be this one. P2 is going to be this one. So P0, P1, P2. If we go in here, this is 0, 1, 2, 3, 4, 5. This is everything. This is everything except for 5 and 1. So this is P1. This is P1. I should have used a different color here. So this we're converting to these two states. We're converting to P0. This we're converting to P1. We're converting this to P2. So P1 includes everything. This includes everything. This is P1. This includes everything. This is P1. 0, 1, 2, 3, 4, 5. This is P1. 0, 2, 3, 4. That is P2. 0, 2, 3, 4. This is P2 and P2. So what we have here is our table to help us construct. We have constructed the table to help us build the DFA. So we can get rid of this down here. Kind of a lengthy video. Okay. So this is the NFA, non-deterministic machine, finite automata, and we constructed this table to convert it to a DFA, which is going to be deterministic. It might not be the most efficient. We might need to minimize it more, but it is going to be a DFA in definition. So what we have is we're going to have a P0 state. It looks like we have three states: P0, P1, and P2. So P0, P1, and P2. You can use this table, kind of don't have to look at these anymore. We can look at these guys: P1, 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 P2, P2, P2. Okay, so from P0 with input A, we can go to P1. From P0 with input A, we can go to P1. From P0 to P2, from P0 to P2, we can get there with input B. From P1 to P1, basically to itself, with input A. So you're at P1, and to get to P1, you can use input A. From P1 to P2, from P1 to P2, we can use input B. From P2 to P1, from P2 to P1, we can use input A. So let's put this on the other side. B. From P2 to P1, we can use input A. And then from P2 to P2, we can can use input B. Now, the other thing we have to look for is final states. So, whatever was a final state in the NFA, so the final state, this was a final state. Q5 is a final state, it's an accepting state. So wherever there's Q5, it's going to be a accepting state. So there's not Q5 in P2. There is Q5 in P1. So P1 will be the accepting state. Hopefully that is not too messy. Okay. So, yeah, so basically this has been converted from an NFA, non-deterministic, to a deterministic machine, finite automata. We should be able to test this. So input AA, if we look at this machine, input A from the initial state, so this is the initial state, this is the initial state, Q0, P0. If we get the input AA, it's accepted by this machine, A, and self loop back to yourself, A. It's in an accepting state as well. So AA is accepted by both grammars. Let's check AAB. So let's go to this one. So A. So using input A, and then B. There's not, it doesn't look like this one accepts it. So you can use lambda, A, B. So AAB is not accepted by this machine, and you can double check that. Let's check out this one. Is AAB accepted? If we have A, and then we can have A, and then B, this is not an accepting state. So we definitely have to use the ticket to get to A, and then we can use a self loop A and then B, but we're still going to be in P2. This is not an accepting state. So AAB is not accepted by both of these machines. And you can kind of check other input strings into the machines. But you can see that we have now converted this NFA into a DFA. So you can see here there's lots of different choices in lambda, and it's non-deterministic. You can see this is deterministic. And it has a lot less states, but it is the same machine. Okay, that's it.